Controlling Acid Rain, Policy Issues by James Afay and Dan Gallum. Policy Discussion Series, MIT L83-012 September 1983. This work was funded by the Champion International Foundation and the Center for Energy Policy Research of the MIT Energy Laboratory, and that support is gratefully acknowledged. The authors also are thankful for the helpful comments of L.C. Cox and J.M. Dauch. Controlling Acid Rain, Policy Issues. James Afay and Dan Gallum. Energy Laboratory, Massachusetts Institute of Technology, Cambridge, MA 02139. Abstract. The policy and regulatory ramifications of U.S. acid rain control programs are examined, particularly the alternative of a receptor-oriented strategy as contrasted to emission-oriented proposals. For example, the Mitchell Bill, which set sulfur emission reductions to uniform national levels. In receptor strategies, goals for deposition reductions in ecologically threatened areas are determined and the emission reductions are apportioned primarily to sources that cause the bulk of acid deposition in those areas. It is very likely that a receptor-oriented strategy would be less costly, on a national basis, than a uniform emission reduction strategy, and certainly more beneficial to the endangered areas. For a receptor-oriented strategy, a detailed economic analysis needs to be performed to select the least cost emission control method for the individual sources. Such methods may include scrubbers, combustion modification, total or seasonal fuel substitution, and electricity import, i.e., emission export. An emission control scheme tailored for northern New York and New England would also benefit sensitive areas in southeastern Canada, and thereby help to diffuse the present U.S./Canadian impasse over acid rain control agreements. Table of Contents. Abstract I1. Introduction I2. The Acid Rain Problem 2-3. Current Acid Rain Control Proposals 4-4. Relating Emissions to Deposition 6-5. Alternative Acid Deposition Control Strategies 7-6. Policy Implications of Alternative Strategies 10-7. Transboundary Acid Rain Problems 14-8. Conclusions 16. References 18I. Introduction. Acid rain caused by copious emissions of sulfur and nitrogen oxides during the combustion of fossil fuels, is said to damage natural ecosystems in acid-sensitive areas downwind of heavily industrialized regions of North America and Europe. To mitigate such damage in the northeastern US and eastern Canada, a substantial reduction of the precursor emissions, SO2 and NOx, would be required. Complete elimination of such emissions is out of the question, and substantial reductions, while technologically feasible, would be very expensive in the aggregate. Significant emission reductions could be achieved in the distant future by phasing out existing high-emission sources and replacing them with new facilities that use either low-emission fuel or novel emission control technology. In the meantime, cleaning up existing facilities will be difficult and expensive, since that requires retrofitting and modification of time-honored and proven processes. In many instances, the lack of a suitable retrofit technology and of storage and supply routes for cleaner fuels impedes emission reductions. Nevertheless, in the near future, 1 to 2 decades, the bulk of emission reduction can only be obtained from existing sources. Currently debated proposals and bills introduced in Congress, for example, the Mitchell Bill, S-146, Congressional Record, 1983, aim at a partial emission reduction across most of the 31 states east of, or bordering on, the Mississippi River. As shown in an accompanying paper, Fay, Gallum, and *, the term acid rain is somewhat of a misnomer. Acid precipitation is a better term, as snow, fog, dew, hail, etc., all may contain acidic matter. The distinction should also be made between wet and dry deposition. The latter term is the adsorption and absorption of dry vapors and particles on soil, water, vegetation and structure. 2 Grull, FGG, 1983, such partial, across-the-board emission reductions of only one of the acid rain precursors, so too, would reduce the average precipitation acidity very little. There is a more cost-effective approach that could benefit environmentally sensitive areas to a greater extent, which we term a targeted strategy. The elements of a targeted strategy are identifying sensitive areas which will benefit from a reduction of acid deposition, 2. Determining target levels of deposition reduction needed, 3. Relating the geographical distribution of emission reductions to the reductions of deposition in sensitive areas, and 4. Selecting mitigation methods, their cost and manner of implementation to minimize aggregate costs. While a targeted approach may not benefit all impacted areas equally, the allotted resources can be brought to bear more effectively on protecting, at least in the interim, the most sensitive areas. As new combustion and emission control technology is developed, greater emission reductions could be achieved among all source areas, thus increasing the protection of other sensitive areas as well. In this paper, some of the technical aspects and policy ramifications of a targeted acid rain control strategy will be explored. 2. The acid rain problem. While it has been known for more than 100 years that precipitation sometimes is quite acidic, only within the past decades has there arisen a recognition that acid precipitation deleteriously affects natural ecosystems, especially aquatic life. Since World War II, first FLM_2 FL*HY3 in Scandinavia and then in northeastern North America, monitoring of precipitation acidity and aquatic ecosystems has shown some evidence of increasingly severe aggregate effects. The acidity is principally associated with sulfate and nitrate ions in precipitation. These ions are formed from the oxidation of sulfur and nitrogen oxides, SOx and NOx, in the atmosphere, whose principal sources are the products of combustion of fossil fuels. Because these atmospheric oxidation reactions proceed very slowly, the deposition of sulfate and nitrate ions occurs at great distances from the point where combustion effluent is injected into the atmosphere. In the northeastern U.S., the present average precipitation acidity is pH 4.2, but spatial and temporal fluctuations of *1 pH unit have been observed. Map 3S/rain, 1982. Acid precipitation is most noticeable near regions of heavy industrial activity, such as Western Europe and Eastern North America. Within such identifiable areas, estimates of SO2 and NOx emissions show a 10-to-1 preponderance of man-made emissions over biogenic sources. In the US, about 90% of anthropogenic sulfur is released in the combustion of fossil fuels, about 2/3 of this by electric generating stations. Of the total sulfur released into the atmosphere within the eastern US, about 20% ends up in acid precipitation and 80% in dry deposition and convective transport by the wind beyond the region's boundaries. Gulam, 1983. A similar proportioning of deposition and transport also holds for nitrogen oxides. Of the emission sources of NOx, vehicles, principally the automobile, account for nearly 1/2. In terms of acidifying potential, aggregate SOx emissions constitute about 2/3 of the total and NOx the remaining 1/3. YSL4 aquatic ecosystems are adversely affected by acidification. The effects may depend on the kind and proportions of anions and cations in precipitation rather than simply on the net hydrogen ion concentrations. Many lakes in the northeastern US and eastern Canada have been markedly affected by acid precipitation because of the lack of natural buffering capacity, the underlying geologic structure being granite rather than limestone. Other terrestrial ecological effects are suspected, such as forest growth stunting and disease, but the evidence is not unambiguous. Because acid precipitation is widespread, sensitive receptor areas can be identified by surveying for the early signs of ecosystem deterioration, principally aquatic populations. It is these sensitive areas which would be the principal beneficiaries of reductions of acid precipitation. Overlaying the maps of poorly buffered areas and present acid deposition contours, it can be shown that the exposed sensitive areas are confined to Upper New York State, New England, Southern Ontario and Quebec and parts of the Smoky Mountains, FGG, 1983. 3 current acid rain control proposals pending legislative proposals, for example, the Mitchell Bill, for reducing acid rain impacts are oriented toward controlling utility sulfur emissions to a nearly uniform level, expressed as sulfur emissions per unit of fuel heat, throughout a 31-state area of the eastern U.S. **. The unstated concept is analogous to that of controlling a metropolitan urban **. These proposals focus on sulfur emissions, but allow credit for reductions of nitrogen oxide emissions. They reflect the much greater difficulty of achieving significant reductions of nitrogen oxide emissions and the uncertainty as to whether nitrate acidity is as harmful to ecosystems as sulfate acidity. I_II to 3 3 high 25 where source emission reductions to a uniform emission standard would result in a commensurate reduction of ambient pollutant levels to values that are more or less uniform throughout the EST. More significantly, the final level of emissions permitted under the Mitchell Bill is an equitable one in the sense that each source, on average, would be allowed emissions in the same proportion to fuel used. Admittedly, the abatement costs to achieve such a level of reduction would be quite different among the various sources, the greater cost being incurred by sources which must reduce emissions the most. If implemented, it is estimated that the Mitchell Bill would result in a reduction of 45% of the SO2 emissions in the eastern U.S. from the present level of 22.5 MTY1, Friedman, 1981. This goal would be achieved over a 10-year period principally by retrofitting flue gas scrubbers to existing power plants, and to a lesser extent by removing sulfur from coal through cleaning and by replacing high-sulfur coal with low-sulfur coal. More advanced technology suitable for new plants would not be widely available within the 10-year time limit. This proposal implies a proportionate reduction of acid sulfate deposition. Using atmospheric models, FGG, 1983, estimate that a proportionate sulfate deposition reduction would indeed be expected in the Adirondacks, an environmentally sensitive area. But because nitric oxide emissions would not be reduced, the expected average increase of rain pH would be less than 0.2 units to pH 4.3-4.4. In contrast, a report of the National Research Council, NRC, 1981, recommended that a desirable average precipitation pH would be 4.6-4.7. Such levels could only be achieved by almost complete elimination of sulfur emissions, or by substantial curtailment of both sulfur and nitrogen emissions. Since LTLLLI2KLL6, the Mitchell Bill does not explicitly suggest a goal for the amount of reduction of acid deposition. It is not clear what the proposers expect regarding environmental improvements following the mandated sulfur emission reductions. These reductions are by no means inexpensive. Various estimates place the annual costs of the Mitchell Bill in the range of $3 to $8 billion. Friedman, 1981, FGG, 1983. For relating emissions to deposition, the ultimate goal of any acid rain mitigation strategy is the reduction or elimination of the ecological impact of acid deposition, its effects on aquatic systems, forest crop productivity, potable water supply systems and materials damage. but these adverse effects are mostly confined to the so-called sensitive areas and are most prominent in the very northeastern corner of the US and eastern Canada. A better measure of the efficacy of any strategy would be the reduction of deposition achieved in sensitive areas rather than the aggregate reduction of emissions. A receptor-oriented strategy requires the setting of a goal for the reduction of acid deposition in sensitive areas. Such a reduction would be based on an acid deposition standard which would ensure that long-term environmental damage will not occur. The relationship between acid deposition and ecological changes are presently not well defined. Recent surveys indicate, however, that a minimum annual rate of deposition of acid sulfate can be used as a criterion for protection of sensitive ecosystems from further damage. NRC, 1981, NRC Canada, 1981, Stockholm, 1982. Deposition reduction goals for all sensitive areas can then be constructed by tailoring emission reductions to meet this criterion. Tailoring emission reductions to achieve maximum environmental benefits of acid deposition reductions requires the use of source-receptor relationships derived from meteorological models. These models confirm the intuitive concept that acid deposition at a receptor site is more affected by a nearby source than by a distant source of equal strength. Long-range transport models provide a quantitative measure of the relative contributions of nearby and distant sources to local acid deposition. At present, atmospheric models are not recognized by all experts as valid policy tools for emission reduction allocations. NRC, 1983. Our analysis showed that in regard to annual average airborne sulfate concentrations there is substantial agreement between 8 models used by the U.S. Canadian Work Group on Transboundary Air Pollution, FAE, 1983. Further model improvements and the incorporation of NOx chemistry should strengthen the basis of using atmospheric models for allocating emission reductions in the source areas. 5 alternative acid deposition control strategies. We now turn to the question of how emission reductions, however allocated, can be accomplished. For existing sources, the technological alternatives are 1. Removal of sulfur from the fuel before combustion, 2. Removal of sulfur during combustion, 3. The substitution of low sulfur for high sulfur fuel, and 4. The removal of sulfur dioxide from flue gases. Techniques for removing sulfur during the combustion process, for example, fluidized bed combustion, FBC, lime-injected multistage burner. It should be noted that the progressively lessening influence of distant sources by no means implies that acid deposition at a specific receptor is all caused by local, for example, intrastate sources. The scale length of ACT deposition is a few hundred kilometers. 8 lim are not yet fully developed for large-scale commercial use and would require replacement of the steam generator, a major component of an electric power plant. Thus, it is doubtful that existing sources can be modified in time to utilize these novel methods. Removing sulfur from the flue gases by scrubbing requires a substantial add-on facility to existing plants, called retrofit. Not all plants can be so modified for lack of space and waste stream disposal area. Other modifications to fuel handling and flue gas processing systems, for example, fly ash precipitators, may also be needed. While certainly not universal panaceas at present, scrubbers are perhaps the most widely applicable to existing facilities. Modern utility and industrial boilers are designed to use a specific fuel type. For example, it is not possible to burn gas efficiently in a boiler designed for coal. Even substitution of low for high sulfur coal would require modifications to the coal handling equipment and the electrostatic precipitators. While it is possible to consider the replacement of high sulfur by low sulfur fuels, the potential for such substitution and the costs, both average and marginal, will depend on the myriad difficulties to be surmounted in a large number of non-identical plants. It will not be simple to implement a control strategy which induces many users to change fuel type. Because of the variable effects on sensitive areas of nearby and distant sources, there are other management schemes that could lessen the deposition in sensitive areas. Emissions could be shifted to more distant locations by importing electric power to the source areas. This could be accomplished either by use of surplus generating capacity in the more remote regions or by constructing new or replacement plants for export of power to the source areas. An interchange of low and high sulfur fuels between proximate and more remote areas would also move sulfur emissions further away from sensitive areas. The least emission dispatch, LED, method. Finally, one may use when decreased acid deposition is desired. For example, during high pollution episodes, the electric generating plants with highest emissions could curtail output or shut down completely, while those with lesser emissions, for example, oil and gas-fired power plants, take over the excess load. Of course, it is not at all certain that such measures would be less costly than reducing emissions from present sources by use of emission control technology, but they do provide some potential for reducing deposition beyond the recourse to installing elaborate equipment. There are potential environmental and economic benefits if emission reductions were timed to the season of the year and possibly even to the appearance of high pollution episodes. Observations of the seasonal patterns of acid deposition show that sulfate deposition is much more pronounced during the summer half of the year. The use of low sulfur, and generally expensive, fuels during these times would still be less costly than their year-round use, or installation of emission control technology. Another summer phenomenon is the persistent elevated pollution episode in which acidic and other atmospheric contaminants build up to high levels whereupon they are scavenged by rain, resulting in a highly acidic rainfall. If such events could be forecast, the use of clean fuel just prior to and during such episodes might reduce the large increments of deposition. Any substantial reduction of sulfur emissions, whether that contemplated by current legislative proposals or the suggested 10 alternative schemes, will require about 10 to 20 years for complete implementation. Limitations on the productive capacity of equipment suppliers and on capital markets to provide financing mean that changes will have to be phased in over a period of years if costs are to be contained. Planning and execution of major modifications to a large source require several years. In order to secure the most immediate environmental benefits, modifications to facilities in the source area of the primary impacted areas should receive first priority. Over a long period of time, perhaps 30 years or more, a significant reduction of sulfur and nitrogen emissions below present levels would result from the replacement of existing plants or combustion systems by new ones which would have to meet new source performance standards, NSPS. Even with some growth in fuel usage in the eastern U.S., aggregate sulfur and nitrogen emissions should decrease because the NSPS emission standards are considerably more stringent than the average present emission levels. On a shorter time scale, 10 to 20 years, the emission reduction must be exacted from existing sources. 6 Policy implications of alternative strategies. Emission-oriented acid rain control proposals, such as the Mitchell Bill, would set a more or less uniform sulfur emission standard, for example, 1.2 ipso-2 per million BTU, which is less stringent than the NSPS standard. This approach is consistent with the principles of the Clean Air Act in that it establishes a uniform emission standard throughout the country. Such a policy supports the protection of regional air and rain quality irrespective of local air quality regulations. Uniform emission standards would prevent individual states from allowing, 3 excessive emissions and thereby gaining a competitive advantage over other states whose regulations may be more stringent. By linking sulfur emissions to fuel heat value, the Mitchell Bill departs in detail from the NSPS goal, which requires the use of sulfur removal technology even for low-sulfur fuel. Nevertheless, the emphasis on interstate uniformity of specific emission rates is consistent with historical precedents. The Mitchell Bill incorporates some flexibility. Neighboring states may trade emission reductions provided the aggregate emissions are not increased. Such variation is also recognized under the current bubble concept. Within a given plant or ESHT, emissions may be increased above applicable emission standards from some sources provided they are reduced by other sources and the aggregate levels are not increased. The objective of such a policy is to permit less costly ways of controlling aggregate amounts of emissions, with the assumption that the redistribution of emissions does not deleteriously affect air quality. What we know about acid rain calls into question the efficacy of these traditional policies. How the reductions of sulfur emissions are distributed within the bubble encompassing the eastern US and Canada very much influences the environmental benefit of specific sensitive areas. Environmental effects are not indifferent to the way aggregate emissions are parceled out. Although it is true that uniform emission standards would temper interstate competition to exploit local variations in emission standards, there is sufficient reason to consider more appropriate policies for acid rain mitigation than uniform standards. A uniform emission standard is not likely to lead to a least cost policy for controlling acid rain deposition in sensitive areas. Where aggregate costs may become very large, which is very likely for any acid rain control policy, the savings to be realized in a targeted approach may be quite substantial. Emission reduction strategies tailored to achieve desired deposition reduction in sensitive areas must still employ suitable criteria for allocating reductions. Two criteria are suggested: cost and equity. If aggregate costs are minimized for a given level of net deposition, then source reduction will be allocated to a level where the marginal cost of deposition reduction will be the same for all sources. This implies a greater marginal cost of emission reduction for nearby sources compared with distant sources. On the other hand, an equity principle might be invoked, such as equal deposition per unit of fuel heat for all sources, for example, FGG, 1983. A receptor-oriented strategy which minimizes acid deposition in sensitive areas may impose higher marginal and average costs of sulfur emission reduction on sources closer to sensitive areas, as mentioned above. Because marginal costs increase with the level of emission reduction at any source, more stringent and expensive control will be needed near sensitive areas than at more distant locations. Although no detailed analysis has been made, it seems likely that the increments in the cost of electric power and industrial heat which will result from the implementation of such a strategy will be greatest for those sources proximate to sensitive areas, and certainly greater than would be imposed by a uniform emission reduction policy. Thus, while aggregate costs for the region, or nation, would be less for a receptor-oriented strategy, some sources may experience larger costs. Given the unique nature of the acid rain problem, it may be necessary to modify the traditional policy of requiring each polluter to bear the 13 full costs of his own abatement. The allocation of emission reduction which would minimize aggregate costs would require very stringent and expensive control systems for sources near sensitive areas. It has been suggested that a trust fund financed by a regional or national tax on the consumption of electric power could underwrite all or part of the capital costs of control equipment retrofitted to existing plants for the purpose of meeting the allocation requirements. Parker, 1983. An alternative source of trust funds would be a sulfur emissions tax, which would have the added benefit of providing an incentive to reduce emissions as well as a recompense for operating costs if only capital costs are to be paid from the trust fund. Even though it may not be entirely equitable, a trust fund may be a practical necessity, considering the substantial costs any acid rain mitigating strategy will entail. Reducing emissions by replacing eastern high-sulfur coal with western low-sulfur coal would have significant economic, social and political ramifications. Loss of employment and production in eastern high-sulfur coal mines would add considerably to the burden of communities already impacted by the decline of smokestack industries. On a national scale, there would probably be a net loss of mining employment and perhaps total employment. Eastern coal mining states will oppose the export of mining activity to western states because of the adverse local economic and social impacts. The infrastructure improvements required for such a shift and the possibly smaller increase of electricity cost compared with other alternatives for emission reduction will be seen in these states as not compensating in amount or kind the loss of coal mine production. 14.7. Transboundary acid rain problems. A major element of the U.S. acid rain problem is the Canadian view that acid rain precursors emitted from U.S. sources drift across the U.S.-Canada border and contribute to acid deposition in southeastern Canada, an ecologically sensitive area. Damage to Canadian lakes and forests could have a significant economic impact in these provinces. While not denying a similar effect in the U.S. from Canadian sources, Canada is urging prompt action for reducing sulfur emissions throughout eastern North America. The cumulative observations of acid rain damage to aquatic systems in the northeastern U.S. and southeastern Canada and the realization that the sources of acid rain precursors could be quite distant from the border, and on both sides, created the need for international consultation on methods for control of acid precipitation. In June 1978, an exchange of notes created the U.S. Canada Research Consultation Group on Long-Range Transport of Air Pollutants. This was followed in 1979 by a joint statement on transboundary air quality which expressed the determination to reduce transboundary air pollution and to seek bilateral agreements on control measures. A year later a Memorandum of Intent, MOI, was agreed upon, detailing plans for further negotiations and the exchange of scientific and technical information, principally on the problem of acid rain. A coordinating committee was established and scientific work groups were appointed to assist the coordinating committee, McLure, 1983. The export of acid rain precursors appears to be more detrimental to Canada than the U.S. According to one estimate, Galloway and Whelpdale, 1980, 14% of U.S. sulfur emissions flow into Canada while 33% of Canadian emissions flow in the reverse direction. But because U.S. sulfur emissions are 7 times those of Canada, the flow into Canada is 3 times the reverse flow into the U.S. At the present time there is no estimate for the respective rates of acid deposition due to the transboundary flows of precursors. If these estimates are correct, then the import of acid sulfate to Canada is 75% of Canadian emissions, the comparable U.S. import is 6%. Even though deposition ratios may be different than transboundary flows, it is clear that Canada cannot greatly ameliorate its acid rain problem without a substantial U.S. effort of curbing sulfur emissions. But with respect to environmentally sensitive areas in upstate New York and New England, the U.S. would noticeably benefit from Canadian emission control. One study, Environment Canada, 1981, estimates that 30% of acid sulfate deposition at an Adirondack receptor is caused by Canadian sources. On the other hand, a joint U.S./Canadian emission control scheme targeted toward the protection of northern New York and New England would also benefit the sensitive areas in southeastern Canada. The Canadian sensitive receptors lay in the lee, so to speak, of the U.S. receptors in regard to the prevailing acidity-bearing air trajectories. These studies indicate that the transboundary flows of precursors and the acid deposition component due to precursor imports are significant factors in the evaluation by each country of the expected benefits from emission control programs. Certainly for Canada and possibly for the US, an acid rain mitigation strategy which is not mirrored on the other side of the border will not be fully effective. But more important to future U.S. Canada negotiations will be an acceptance of estimates of source-receptor relationships as the basis for an equitable distribution of emission reductions on both sides of the border. 8 conclusions. Given the very substantial cost of any significant reduction of emissions of acid rain precursors, an efficient national acid rain control policy should be receptor rather than emission-oriented. Such a policy is likely to be less expensive and would benefit the impacted areas to a greater degree. It would concentrate the emission reduction in those source areas that deliver the bulk of acid deposition to the environmentally sensitive regions. In contrast, the traditional policies of uniform emission standards across the nation, as exemplified by proposed acid rain legislation, are likely to be more costly and less effective. In addition, a receptor-oriented policy could produce more immediate results in reducing acid deposition than the long period, 1 to 2 decades, required for implementation of a uniform emission reduction program. A limited receptor-oriented approach would also permit a timely appraisal of its success, such as a measurable reduction of wet ion deposition at the selected receptor, before vast expenditures are sunk into a uniform source-oriented approach. To secure the savings inherent in a receptor-oriented policy, a variety of emission control technologies and management alternatives must be evaluated on a source-by-source basis. In addition to the standard techniques of fuel cleaning, flue gas scrubbing and combustion modification, other possibilities, such as seasonal and episodic fuel substitution, least emission dispatch and electricity import should be considered in arriving at a least cost emission reduction scheme. The proximity of some environmentally sensitive areas in the U.S., such as northern New York and New England, to equally sensitive areas in Canada provides a basis for a mutually reinforcing receptor-oriented 17 strategy in both countries. The mutual benefits of targeting emission reductions in source areas adjoining the international border could become a strong incentive for reaching an international agreement on this important transboundary pollution problem. M3 OLL 6210L132LL1118 References Congressional Record, Senate, 1983. Description of acid rain legislation introduced by Senator George J. Mitchell, Washington, D.C. 20510. Environment Canada, 1981, Impact Assessment of Acid Deposition Interim Report, Ottawa, Canada, CIACP. Fay, J. 1983, Long-Range Transport of Acid Rain Precursors MIT Energy Laboratory, Cambridge, MA 02139, MIT L83-005. Fay, J. Gulam, D. and Grull, J. FGG, 1983, Controlling Acid Rain MIT Energy Laboratory, Cambridge, MA 02139, MIT L83-004. Friedman, R.M., 1981, Testimony before the Senate Committee on Environment and Public Works Proposed Legislation, S1706 and S1709, related to Acid Precipitation Control Office of Technology Assessment, U.S. Congress, Washington, D.C. 20510. Galloway, J.N. and Whelpdale, D.M., 1980, Atmospheric Sulfur Budget for Eastern North America. Atmospheric Environment, 14, 409-417. Ghulam, D. 1983, Acid Deposition, Precursor Emission Relationship in the Northeastern U.S., The Effectiveness of Regional Emission Reduction. Atmospheric Environment, 17, 1387-1390. McClure, J. 1983, North American Acid Rain and International Law. Fletcher Forum, 121-154. Map 3s/rain, 1982, the Map 3s/rain Precipitation Chemistry Network, Statistical Overview for the period 1976-1980. Atmospheric Environment, 16, 1603-1633. National Research Council, NRC Canada, 1981, Acidification in the Canadian Aquatic Environment. Ottawa, Canada. Kaya 6. National Research Council, NRCU.S, 1981, Atmosphere-Biosphere Interactions, Toward a Better Understanding of the Ecological Consequences of Fossil Fuel Combustion. Washington, D.C. 20418. National Research Council, NRCU.S, 1983, Acid Deposition, Atmospheric Processes in Eastern North America. National Academy Press, Washington, D.C. 20418. Parker, L.B., 1983, Distributing Acid Rain Mitigation Costs, Analysis of a 3 mil user fee on Fossil Fuel Electricity Generation. Congressional Research Service, Library of Congress, Washington, D.C. 20540. Stockholm, 1982, Conference on Acidification of the Environment, Report from the Expert Meetings, available from the Swedish Environment Protection Board.